In this video, I will teach you how to take the derivative of inverse trig functions like arctangent, arcsine, and arcsecant. If you appreciate the content, please give it a like. I'd like to make an analogy to help you understand why inverse trig functions have restrictions. X squared equals 9 has two solutions. Taking the square root of both sides, we know that x can equal positive 3 or negative 3. That's two solutions. On the other hand, when you're given the equation x equals the square root of 9, we understand that this only means the one solution of x equals 3. The output values are restricted to only the positive solutions. Similarly, when we solve the equation cosine x equals 1/2, we find that this equation has two solutions. We have memorized that the cosine of pi over 3 is equal to 1/2, but that's just the reference angle. A reference angle is the angle between the terminal side and the x-axis. Every quadrant has an angle with a reference angle of pi over 3. However, cosine is the x value on the unit circle, and we want cosine to be positive in this case. So we will restrict ourselves to quadrants 1 and 4, where cosine is positive. So the two solutions to this equation are x equals pi over 3, the reference angle, and this angle in the fourth quadrant, which is 5 pi over 3. So, similar to when we solved the equation x squared equals 9, we found two solutions that satisfy this equation. However, if you isolate the x, you get x equals arc cosine of 1/2. This is only understood to have one solution. There's this artificial restriction on the output values, the range. When it came to x equals the square root of 9, the restriction was only the positive solution, not the negative. Each inverse trig function has its own set of restrictions, and you just have to memorize them. The output values for arc cosine are only allowed to be in the first and second quadrants between 0 and pi. The output values for arcsine are only allowed to be in the first and fourth quadrants between negative pi over 2 and positive pi over 2. The range for arctangent is almost the same as for arcsine, except the endpoints are not included. Tangent is not defined at negative pi over 2 and positive pi over 2, so we had to leave those points out. So, what is the value of arc cosine 1/2? Only the solution pi over 3 falls within the restricted range of arc cosine. So that is the only answer, x equals pi over 3. I want to emphasize one more time that inverse trig functions will always have one answer, never more than that. So how do we find the one value of arcsine of negative 1/2? To evaluate an inverse function, in general, we ask ourselves f at what is equal to this number. To evaluate arcsine of negative 1/2, you ask yourself the sine of what is negative 1/2. For a moment, ignore the negative sign and just ask yourself the sine of what is 1/2. Make sure you have memorized these 9 trig facts, including the fact that the sine of pi over 6 is 1/2. That tells us that the reference angle is pi over 6, and here are the two angles within the restricted range with a reference angle of pi over 6. However, in this case, we want sine to be negative, and sine is the y value on the unit circle, so that means fourth quadrant only. But be careful. We would normally think of this angle as 11 pi over 6. But that means we are thinking of this angle as starting from 0 radians and rotating all the way around and back to this position. That takes us well beyond the maximum range value of pi over 2. So, how do we get to this position without going outside of the restricted range? We have to rotate in the clockwise direction, and therefore this angle is negative pi over 6. So that is the one solution. By the way, there is a second notation for expressing inverse trig functions involving this -1 superscript. So this notation means arcsine, this is another way of writing arccosine, and this is another way of writing arctangent. I usually stick to this way with the arcsine, arccosine, and arctangent because when students see this notation with the little -1, they often mistakenly think that this means 1 over sine x, which would be cosecant. But this is not true. These are not the same. This little -1 doesn't mean 1 over. It means arcsine. It means what we've been doing. Pause the video and evaluate these last two inverse trig functions. To evaluate arccosine of radical 3 over 2, you ask yourself the cosine of what is radical 3 over 2. We have memorized that the cosine of pi over 6 is radical 3 over 2. So pi over 6 is once again the reference angle. In this case, we want cosine to be positive, so we are going to stick to the positive side of the restricted range. So that's going to be the reference angle itself. And the one value of arccosine radical 3 over 2 is pi over 6. By the way, you should be doing all this in your head. I'm only writing it down for instructional purposes. To evaluate the arctangent of negative radical 3, you ask yourself the tangent of what is equal to negative radical 3. Ignoring the negative sign, we will find the reference angle. The tangent of what is radical 3. We have memorized that the tangent of pi over 3 is radical 3. So pi over 3 is the reference angle. These are the two angles within the restricted range with a reference angle of pi over 3. But in this case, we want tangent to be negative. Tangent is the slope of the terminal side, and the slope will be negative in the fourth quadrant. Again, we would normally think of this as 5 pi over 3. But not this time, because 5 pi over 3 takes us outside of the restricted range. Instead, we have to get there by rotating in the clockwise direction, which is why we will call this simply negative pi over 3. That's the one value of arctangent. One more time, let me emphasize, inverse trig functions will only ever have one value. Now it's time to memorize a new derivative rule, the derivative of arcsine x. So break out those flashcards. I'm going to write the rule with a u instead of an x right here because it normally won't just be an x. It'll be some type of an expression right here. So the derivative of arcsine u is 1 over the square root of 1 minus u squared, and then here comes the chain rule, times the derivative of that inner expression, u prime. Since this is just an x, there will be no chain rule, and y prime, the derivative of arcsine x, will be 1 over the square root of 1 minus x squared. So here's the derivative of arcsine that I gave you before. The derivative of arccosine will be the same thing with a -1 instead of a +1. Here's the rule for the derivative of arctangent, and the derivative of arccotangent will be the same thing with a -1 instead of a +1. The derivative of arcsecant and arccosecant have this extra u out in the front inside of an absolute value. Again, I need you to write these on some flashcards and just study these. You have to memorize these rules. Here are a few silly things that I think in my head to help me keep straight which rule goes with which function. I'm going to start with arctangent. Arctangent is the only one that has a plus in it, and that plus is like a t. T for tangent. Also, arctangent is the only one that doesn't have a square root over the denominator. If you think of the square root as a little blanket, it won't surprise you that you don't cover up with a blanket when you go tanning. Arcsine and arcsecant have derivative rules that are very similar to each other. They both have the square root, but one has 1 minus u squared and the other has u squared minus 1. So how do I remember which goes to which function? If you can remember that arcsecant is the one with the extra absolute value of u out in the front, then I always think to myself, well, these u's, they're friends, they're brothers, they're buddies. They want to be near each other. Aww. So the one that has this extra u out in the front, of course the u squared is going to be over here on the left because, aw, look, they want to be together, you guys. But on the arcsine, the one that doesn't have the extra u, then the u squared can be way over here to the right because it has no friend that it's trying to be close to. Find the x-coordinate or coordinates at which y equals arctangent x over 2 minus 2x has a horizontal tangent line. Make sure you have this association locked in because it comes up over and over again in AP Calculus. Horizontal tangent line means y prime equals 0. So let's find y prime and set it equal to 0. We bring down the constant, and then the memorized rule for the arctangent of u is 1 over 1 plus u squared times u prime because of the chain rule. In this case, the u is x over 2. So we have 1 over 1 plus, and I think I will write it as 1/2 x instead of x over 2, but it's u squared, and then times u prime. So the derivative of 1/2 x is 1/2. And then the derivative of negative 2x is negative 2. This 5 is like 5 over 1. So multiplying straight across, the 5 will end up in the numerator. Let's go ahead and square this term to get rid of the parentheses. 1/2 squared is 1/4, and of course x squared is, well, x squared. On the next step, I'm going to multiply straight across, so I'm going to have 5 in the numerator, but in the denominator, I'm going to do the distributive property with the 2. 2 times 1 is 2. 2 times 1/4 is 2/4, which simplifies to 1/2. So now we have this. We need to simplify this business because we have a fraction inside of a fraction. That's no good for finding the horizontal tangent line. So one way to get rid of the fraction inside of a fraction is to multiply. We are always allowed to multiply by 1 because multiplying by 1 doesn't change anything. So in this case, I'm going to write 1 as 2 over 2. Because if I distribute this 2, 2 times 1/2 is 1. So I will no longer have a fraction inside of a fraction. The 2 from the numerator multiplies by the 5 and makes 10. So now we have this. Quick alternate universe side lesson. I'm going to show you another way to simplify this part of y prime because we all need practice with our algebra skills and some students might prefer this other way. So I'm writing 1/2 x squared as x squared over 2 because for this method it's all about like denominators. I'm going to multiply this 2 by 2 over 2 to make like denominators. So this is really 4 over 2 plus x squared over 2. So we will have 5 over 4 plus x squared over 2. So we have 5 divided by this fraction. How do you divide by a fraction? Well, you multiply by the reciprocal. So that would be 5 times 2 over 4 plus x squared. And I'm sure now you are realizing that this will give us the exact same thing we got before because 5 times 2 is 10. So that's 10 over 4 plus x squared. We need to continue to simplify this expression by making all of this into one fraction. We can do that by making like denominators between the 2 and the rest of it. So let's multiply by 4 plus x squared over 4 plus x squared. We can now combine these over the common denominator of 4 plus x squared. We need to get rid of the parentheses by distributing. Be careful, because of the negative, I want you to include the negative with the 2. So don't distribute just a 2. Make sure you distribute negative 2. So you should have negative 2x squared right here. A common mistake is to just multiply 2 times x squared and have a positive 2x squared, which will give you the completely wrong answer. Sometimes the hardest part of calculus is algebra. On the next step, we have the like terms of 10 minus 8, which of course is 2. So y prime simplifies down to this. Remember, our goal is to find the x-coordinate of a horizontal tangent line, and we know a horizontal tangent line is where y prime is equal to 0. Label this part of your work like this. A fraction will equal 0 when the numerator is equal to 0. So y prime will equal 0 when 2 minus 2x squared is equal to 0. Adding 2x squared to both sides, we get 2 is equal to 2x squared. Dividing both sides by 2, we get 1 is equal to x squared. I'm going to flip this around. Taking the square root of both sides, we get x is equal to plus or minus 1. We say y has a horizontal tangent line at x equals 1 and x equals negative 1 because y prime equals 0. Part B. At the x-coordinates we found, does y have a relative min, a relative max, or neither? Justify your answer. Here is our expression for y prime from part A. Since y prime is strictly a function of x, we can use the first derivative test to identify relative extrema. In other words, we can make a y prime sign chart. Actually, since we are making a y prime sign chart, I think we should factor this completely. 2 can factor out, it's a GCF. That will leave 2 times 1 minus x squared. Hopefully you now recognize 1 minus x squared as the difference of 2 squares, which can be factored even more. So this will factor further as 1 plus x times 1 minus x. Whoops. So this is the version that I will use to build my sign chart. To build a y prime sign chart, we need the critical values where y prime is equal to 0, which is at x equals negative 1 and x equals positive 1 from part A. But we also need to know where y prime is undefined. A fraction will be undefined where the denominator is equal to 0. Hopefully you can see at a glance that 4 plus x squared equals 0 has no solution. X squared is never negative because we're squaring it. So the smallest this term can possibly be is 0. And then we add 4 to that. So this expression has a minimum value of 4. It will never equal 0. So we can actually forget about this. Set up your sign chart like this, with your only 2 critical values across the top in order from least to greatest. Make sure you label the sign chart as y prime. Make a row for each one of these factors. It's actually up to you how many rows you want to make. I like to factor things out completely and make a lot of rows because each one of these rows will be simple to evaluate. But you could make, for example, 2 rows. You could make just 1 row for this numerator and 1 row for this denominator. It's completely up to you. Now we must decide whether these factors are positive or negative in each interval. Of course, 2 is always positive, so that's easy. 1 plus x is equal to 0 at x equals negative 1. This is the only place where this factor might change sign, so we really only have two intervals to consider, left and right. To the left of -1, this expression will be negative. For example, at x equals -2, we'd have 1 plus -2, which is negative. For x values to the right of -1, this expression will be positive. 1 minus x is equal to 0 at x equals 1. To the left of 1, we have test values like 0. If we plug in 0, we have 1 minus 0, which is positive 1. So this factor will be positive in this interval and negative for values of x that are greater than 1. For example, 2. 1 minus 2 is -1. As discussed earlier, this expression will never be less than 4, so always positive. An odd number of negatives means y prime is negative in this interval. Y prime is definitely positive in the middle interval, and again, negative in the final interval. Function y will have a relative max or min wherever y prime changes signs. Specifically, y will have a relative min at x equals -1 because y prime goes from negative to positive. That means y itself went from decreasing to increasing, thus a relative min. Similarly, y will have a relative max at x equals 1 because y prime goes from positive to negative. That means y itself went from increasing to decreasing, therefore a relative max. We say y has a relative maximum at x equals 1 because y prime changes from positive to negative, and y has a relative minimum at x equals -1 because y prime changes from negative to positive. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.